Well, it is a pleasure to introduce Professor Nemethi. And today he will be speaking about multivariable Poincaré series of surface singularities.
Thank you very much for the invitation and for the opportunity to speak at this conference. I will speak about, as the title shows, about the Poincaré series of surface singularities. And actually, I would like to discuss about somehow about both. You will see about Poincaré series, the analytic version and also topological version. I'm convinced also that also the topological version, it's very interesting for topologists, but also the analytic version is rather interesting and important from analytic point of view in the analytic invariance. And I would like to suggest both sides a little bit and also the connections and to discuss the connections with other invariants. So what is actually the general picture? So what I mean by Poincaré or the Hilbert series of some object or some filtration. Usually what we have is a local ring or some C algebra or local C algebra or some analytic space, and then we fix a point and the local algebra, and we consider a filtration, and this filtration can be defined in many different ways using some, I don't know, divisors, or can be used some normalization or evaluative filtration. But let's at this moment just fix a filtration which can be indexed by a lattice. So it's not just one variable filtration, but for any lattice point in ZS, we consider an FL in the local algebra. This can be an ideal. That's not so important. Usually it's an ideal. FL is a ideal given by the filtration, can be an order function of evaluation or something defines the filtration. So what exactly we want to do with this? So this will be for any lattice point we have the FL. This will be increasing in that sense that if L is decreasing, that if L1 is bigger than L2, then the corresponding filtration FL1 is smaller than FL2. And what we will consider is this codimension. So the codimension of the filtration FL of this ideal or the subspace in the local ring. And today in all our discussions, we assume that this is finite. This dimension is finite. Then we consider the Hilbert function. The Hilbert function, we measure exactly these dimensions. So the Hilbert function for any L in ZS, we consider this dimension of O, of the local ring, divided by this ideal or by this subspace. And this will be denoted today by H of L. And then if we want to put all these numbers together in a series, then we write the Hilbert series, and this is the summation over this L, the lattice points H of L, T to the L. This T should be somehow a bigger T. That's maybe it's not so nice how I write it, but yes. So that means basically, maybe we don't see that the T to the L, that is T1 to the L1, T to the L2, Ts to the Ls, where L is the vector L1 Ls as a lattice point. So in basically what we do here, that we fix the lattice, but we fix also base elements E1, Es, and these are the coordinates in that fixed basis. So this is the usual Hilbert function, and it's well known, and this is the main object what we consider, the first main object. The second, what is the Poincaré, because I want to make a distinction between the Hilbert and Poincaré somehow. So let's, yes, indeed, first let's see an example, the simplest example when the rank is 1, that is just the Z, the lattice, and then we have a filtration index by the integers. Usually we have here only the positive integers, but we can consider any situation. Both situations are important and can be considered. And in this case, when we have this, usually in the classical way, we have that graded version. And that means that we want not O over FL, but we want the quotient of FL divided by FL plus 1. And that is what we will call the Poincaré Poincaré series associated with the filtration. So in this case, from the Hilbert, we can go very easily to the Poincaré, to the graded version, because we have immediately this PT, that is the Poincaré equals the Hilbert HT divided, multiplied by 1 minus T to inverse. So this is actually that, of course, that HL minus HL minus 1 is exactly PL, the coefficient of the Poincaré, that is formally written in this multiplication. And in this case, for example, if F0 is 0, or it's no, if F0 is the local ring for negative integers, then it's very easy to recover P from H and H from P. So we have, they are completely equivalent. On the other hand, when we have a bigger lattice, then it's not so evident how to define the Poincaré, and also it's not so evident how to recover H from P. Usually it's not even possible. So let's go step by step. So again, we have the filtration indexed by the lattice. We define the Hilbert series as we defined in the previous page. And then we define the Poincaré series exactly by the analog of this of the previous formula, the multivariable version, that we multiply h of t by this product of 1 minus ti is the inverse, and that is basically the definition of the Poincaré, the multivariable Poincaré series associated with the filtration or associated with the Hilbert series. So in this way, if I write this as a series, the coefficients PL, then the coefficients PL are this summation corresponding to the subsets of 1 to S with some combination, with some sign of HL plus, I don't know if you see this, okay, so this HL plus sum of EIs. Yes, so this is the definition of the Poincaré, and this is what we will consider. So of course that when S equals 1, then we have the old formula, but in general we have this combinatorial expression of the coefficients of the Poincaré in terms of the Hilbert coefficients. So that is the general picture. So again, we have from H P, and that is the definition. So here we have to notice that the multiplication by this term usually, so if I consider in this ring, then that has a non-trivial kernel. So there are some terms where if I multiply those one with this product, then they become 0. So that means that we have some kind of ambiguity. We lose something when we go from the Hilbert series to the Poincaré series. So usually when we want to so in the previous case, in the classical case, what is the additional information what we need to recover the Hilbert? Usually what we have that the Hilbert coefficients are 0 for negative ones, and then the inversion it's easy. But usually we have to be careful. So in general, that's the problem, that we go to the P, then the Poincaré, then we have to discuss, or we have to be careful if we can go back to the Hilbert series or not. When we can recover H from P, then we say that we have an inversion formula. So inversion, that is the inversion step, and usually can be done in all the cases what I will consider today. We will have an inversion formula, but usually they are not completely trivial. So let's see what we want and why exactly I want to go to the PT, because also with HT we can be very happy. So in this is exactly some sections of H0 sections, or sections of some line bundles. If we have a divisorial filtration or given by some geometric filtration, and then from geometric point of view, or from point of view of algebraic geometry or singularity theory or analytic point of view, that's completely fine. But the point is that sometimes, and usually go to the Poincaré, because somehow by some strange reason, some mysterious reason, the coefficients of PT are connected with the topology. So that's exactly what we want to somehow to discuss today. That From HT, we go to the PT and we try to find the topological connection with PT, with the topology of the singularity or topology of the situation. And additionally, we wish an inversion formula how to recover H from P. So these are basically the two steps. If I want to connect with topology, that find the relationships between the H and P, and after that find the relationship between the PT and the topology. So let's see some concrete examples. So I consider curve singularities first. Just of course that the main topic is here the surface singularities, but I start with the curve singularities because just to emphasize that the inversion is completely not trivial, and in the case of curves, in the case of surfaces, the inversion is totally different. So the inversion formula depends on the geometric situation. We need some additional property from the geometry in order to be able to lift, to solve, say, this system that if I have PT, how to recover H. For that solutions to how to lift, we need some additional property of the corresponding situation. So let's see the curve singularities first. So I start with an isolated curve singularity. It's not necessarily plane curve. Yes, so we have the irreducible components, Ci. For each Ci, we consider a local algebra of the Ci, and after that, we consider the normalization. So the normalization of a curve, irreducible curve singularity is Cti. So these are somehow it's as a space, it's the local germ of the line of C. And we have the discrete valuation, the natural valuation associated with this normalization. So these are exactly the orders in terms of order Ti, if we in F. So these are the valuations. They provide the, of course, that they generate. So if we have S irreducible components, then we consider the lattice of rank S. Exactly somehow the coordinates are the orders of TIs, in TIs the valuations. So this means that the lattice point in ZS provides a filtration. Yes, so that exactly the evaluative filtration, that F is in FL if VI of F is bigger than Li. Li is the I coordinate of the lattice point L. So this is a filtration, actually, as in exactly this, with similar properties in the first page. And then the codimension of FL in the local algebra is the Hilbert coefficients HL. And then using the formula of PT, we can, of course, if I multiply by this product, then so we take the graded, multivariable graded version of the Hilbert function, Hilbert series, then we will have the Poincaré series, P of T. So this is now we apply the general picture for this situation of curve singularities, and here for the evaluative filtration. So of course that is everywhere here we have a lot of analytic information, and actually when C is not plane curve, so it's embedded, the embedded dimension of the curve it's high, say it's in C3 or C100, then we don't even see the topology. It's no topology. But if I want to see the topology, then let's go to the plane curves. It's much, so then we really see the connection with the classical topology of the curve singularities. Of course, also in non-plane curve case, it's very interesting and it's a lot of geometry behind, but let's simplify a little bit the situation. So consider the plane curves. Again, C is an isolated curve singularity nodes embedded in the plane. And in this case, the topology, we have also the embedded topological type of the curve singularity. That is, if we have S connected components of the curve, then we have S copies of S1, the link, yes, of the singularity, and that is embedded in S3, and that embedded topological type, that is from topological point of view of the interesting object. So what are the node effects? So how we connect now the topology P? So there is a associated with the topological type with the embedded link, we have the multivariable Alexander polynomial of the link. And the fact is that PT equals, if S equals 1, then dt multiplied by 1 minus t. Otherwise, is S is bigger than 1. So it's the number of components is bigger than 1. Then PT is exactly the multivariable Alexander polynomial. Yes, this is a theorem of Campillo-Delgado-Gusein-Zade. So in this way, PT is identified with the Alexander polynomial, with the topology. And here a little bit more, some facts about the PT or the DT. So right now we know that they are the same. So they actually, in S equal 1, then we have the correction term, but otherwise they are equal. And actually we know that in the case of algebraic singularities, algebraic curves, algebraic links, the embedded topological type is completely determined by the multivariable Alexander polynomial. So that is a complete topological invariant. And I want to, I need to tell this because from this point of view, then we know that PT provides the embedded topological type. From the embedded topological type, of course, that I can consider the embedded topological type of any partial sublink. So for any subset of 1 to S, I can say subset I can consider that subset of irreducible curves, and that provides a sublink, provides a sub Poincaré or sub Alexander polynomial, and that is what we will need in the next formula. So the inversion formula, if I want to go back to the Hilbert function, to the Hilbert series, then is this complicated summation. So it's our we can the big summation of our any sublink, and with some correction term, all that. So we have to consider the Poincaré or the Alexander polynomial of the partial sublinks with this summation, with these correction terms, and that is how we go back. That is the inversion formula. So that is the formula proved by Gorski and myself. So in this way, if we want the Hilbert polynomial, Hilbert function, and yes, that is somehow somehow the codimension, or to measure the sections of corresponding different line bundles given by the or the filtration, to understand this filtration provided by the normalization. Then if we want to recover from the topology, then we have to consider these Alexander polynomials, and by this inversion formula you go back from P, so D equals P, and from P we have the inversion formula, but that is this interesting formula. So let's see here, I added an example. So if I consider this very simple plane curve, x squared a 2n minus 1 type singularity, of course that this has two connected components, x minus y to the n, x plus y to the n. Both of them are smooth, so the components are smooth, but of course that the contact is high here. So the Alexander polynomial, or the P, yes, of the smooth components is just this one. The two variable Alexander polynomial of the two components of C can be computed. This one actually, for the algebraic curves, the Alexander polynomial can be computed using the splice diagram or the embedded resolution graph. It's combinatorially, they are very precise formulas, so it can be computed. And after that, the inversion formula tells us that it's this sum, basically three terms. That is the one smooth component, the other smooth component, and that is for the two components. This the combination of the Alexander polynomials, and it's normalized by T1 here, T2 here, T1 times T2. And after that, you have to divide also by this one, and that is the Hilbert function. So let's go back again, that what we want to, so just to say again what we did here. So we want to have say the Hilbert function, or algebraic valuations, or algebraic geometry of the local singularity. And here we compute PT. We identify PT with the with the Alexander polynomial, with the topology, and after that we need the inversion formula. So in the plane curve case, this runs perfectly because we hit exactly the most important topological invariant, and after that we have the inversion formula. Okay, so let's go to the next step, surface singularity. So in this case, it's not so, I don't say that it's not so nice, probably it's even nicer, but it's not so direct, or it's not so, it's what is the topology, and again, what is the inversion formula. So again, let's start with the normal surface singularity. Everything is over the complex numbers. And again, I want to define now the very first object is the filtration. So what is the filtration? What is the lattice? And after that, yes, we want the Hilbert function. So we consider a resolution, and above the singular point, we have the exceptional curves, and we consider the irreducible exceptional divisor, so the irreducible decomposition of the exceptional divisor, and we consider the lattice generated by them. So we can think about this lattice as just the free lattice Z module generated by the vertices of the resolution graph, or we can think as the divisors, the integral divisor supported by the exceptional divisor, or just H2 of the resolution space. Yes, and this is freely generated by the exceptional curves. So anyway, we have a free lattice, we have a lattice of rank S, where S is a resolution. Of course, here the resolution is not unique, but we fix one, and S is the number of exceptional divisors. Okay, so then we define the divisorial filtration indexed by this lattice. For any lattice point, we consider the set of functions f in the local algebra, such that if we pull back the function, and if we check the multiplicities, the vanishing orders of the function along the exceptional curve, then that should be greater than L. So the vanishing order along EI should be bigger than Li. So this is a ideal the divisorial filtration. We provide for each L an ideal in the local algebra, and we consider this filtration. And the Hilbert coefficients are exactly again the codimensions, and we have the Hilbert series. And that is, in this, it's coded a lot of analytic information, is a very, very rich analytic information is coded in this Hilbert function. And again, by the general principle, we consider the multi-graded Poincaré series, that is the graded version of the Hilbert, by the very same formula. Again, so this is the analytic. So what we want to understand, or from analytic point of view, what we wanted to codify. And I want to here to emphasize that it's not just say sections we measure by this, how it's the very definition, but also a lot of H1 of line bundles. For example, I just wrote here a formula that this is the coefficient HL. So for an L, of course, that here, actually here, if I want this formula, then I need L to be effective, but it's not so important here. So here is the coefficient, the Hilbert coefficient, Hilbert function. That is chi L is a topological invariant. That is the Riemann-Roch expression. So I don't know if you see, or maybe I put in this. So this is the Riemann-Roch. Sorry?
We can see it.
You see it. So that is the Riemann-Roch expression. So that is a from the resolution graph one can recover. So maybe I should explain here that is on this lattice generated by the exceptional curve, because that is an H2 or is the divisor lattice. We have an intersection matrix. That is a negative definite intersection matrix. That is what is considered here. And Kx is Kx tilde is the canonical class, yes, of the X tilde. Of course, that by this definition, it's analytic, but by adjunction formulas, that actually is topological. How Kx intersects any lattice element or any EI, that by junction formula is topological. So basically, this is a topological expression. So that is chi of L. On the other hand, PGX is its analytic invariant is the geometric genus. Later, probably will be discussed. I will in some other formats will appear. So that is H1 of the structure sheaf. That is the most important, the first analytic invariant which is considered and is very important. So again, just I want to explain or give an example that how the Hilbert function enters in complicated expressions. So this is an H1 of a line bundle given by the lattice point. So that is, yes, associated with that divisor, and we have such a formula. So this HL or the Hilbert function is very important from analytic point of view. And again, so what is our goal? That we need or we wish to understand this HT from analytic or sheaf theoretical point of view, but we go to the PT and we have to know, we have two questions. The first question is that what is, from topological point of view, indeed, no, this PT makes sense, or can we connect with topology or not, or is just in this dimension we don't have this connection. And also, if this PT makes sense from topological point of view, then we need also how to invert, so that how to go back from PT to HT. Yeah. So first, let's consider the inversion formula, just to be sure that PT and HT contain the same amount of information. So again, we have this negative definite intersection form. So we have the lattice. The lattice supports an intersection form because it's in a 4-dimensional X tilde. We have the H2s, and we consider here the cone. That is the anti-NF cone. So these are all the cycles which intersected with the base elements EI, they are negative. So for this, I need also to fix the base elements. They are naturally identified by the exceptional, irreducible exception curves, and they define this cone. This is called also the Lippmann cone. So what is the point here that, and this will be used in the next expression, that using the fact that the intersection matrix is negative definite, turns out this cone is given by these inequalities. It is in the first quadrant. Actually, it's even smaller than the first quadrant. So all the generators, the positive generators of the cone, have all the entries, all the entries are strict positive. So what they generate, they are in the first quadrant. Strictly in the first quadrant, the generators. So also this S it's in very nicely situated in the first quadrant. Why is this important? So the second is this is the first fact. What I will use the second fact. It turns out that the PT. So PT was defined using using this multiplication H by multiplication by HT, and this. It's not so evident that what is the support of this, but it turns out that this PT is supported in this Lippmann cone, is this anti-NF cone. So if a coefficient is non-zero, then that should be in the Lippmann cone. So outside of the Lippmann cone, PL is 0. So somehow this is really, it's a series like in a cone, in a small cone. So then the inversion formula it's what is written here, that H of L, so again, we want to recover H from P. So H of L is this summation. So what is the meaning of this? That if I want H of L and it's L somewhere, actually I put it in the Lippmann cone, but doesn't matter where it is, then we have to consider all the elements which are not greater than L, and we make the summation. But if an element should be also in the support of P, so should be in the Lippmann cone, and also should satisfy this inequality that is not greater than L, then this is finitely supported. So actually this summation is a finite sum, and then this is the inversion formula. Just look at this, that this is completely different as in the curve case. And it's very interesting that it's somehow very naturally appear this kind of shapes where we have to make the summation. It's not given by, I don't know, degrees or something. It's this very interesting shape. This is where we have to make the summation of P, and then we recover H. So this is the inversion formula. The second step, what we want to understand is the relation with the topology. So right now, so the next is what I mean by topology. Yes, in this case, so this is what we want now to discuss, that if I can relate or I cannot relate the PT with the topology. But so by topology, I mean in the case that when X is a normal surface singularity, then it's the link. Link is the, so if I intersect X with a small sphere and X is embedded somewhere in some, I don't know, higher dimensional space, we consider the small ball around the singularity, we intersect X with the sphere, and that will be an oriented three-manifold. So that is the link. And the topology of the singularity actually means the topology of this three-manifold. This can be recovered also using the resolution graph. If I fix a resolution, then the exceptional curves are coded by vertices, the intersection points or intersections of the exceptional curves by edges, and in that way, the self-intersections by Euler decorations, Euler number decorations, and we have a resolution graph. In our discussion, no, I will, in some cases, most of the cases, we assume that this link as a three-manifold is a rational homosphere. So the rational homology is the same as the homology of the S3. So that means that the first Betti number and the second Betti they are 0. This in the language of graph means that the graph is a tree of pi-1s. All the exception curves are pi-1, and then the intersection graph it's a tree. And in this case, the topology actually, it's the three manifolds is completely determined by this lattice and the intersection 4. So what I want now, so what I want to define, I want to define a Poincaré. Of course, that I don't claim that what I define now, it's exactly our Poincaré what was defined analytically. Just I want to define combinatorially or topologically multivariable series. And for this, I need the dual basis of EIs. So there's, in terms of this intersection matrix defined, actually it's negative of the Kronecker delta. We prefer to define this because the intersection form is negative definite. And if I define in this way with negative delta ij, then all the entries of EI stars will be positive. So actually these EI stars, they are the generators of this Lippmann cone. So they are exactly here. On the other hand, we have to be careful about this because the intersection matrix in general is not unimodular. It's non-degenerate, but the determinant is not plus minus 1. So this solution, actually the output of this solution, so the dual basis, it's usually it's rational, it has rational coefficients. So these are the coefficients are positive rational numbers in the EI basis. So we consider, so they are as divisors, they are rational divisors supported by the exceptional curve. So then we define a topological candidate for PT. So just we define combinatorial something, and this is the formula. So it's the product of all the vertices or all the exceptional curves. And again, with using the same notation that T to the sum, but no, this is a rational lattice point. And this kappa I is the valency of the vertex I. So that means that how many neighbors, the number of neighbors of EI. You see, so we have these rational functions for the endpoints and vertices. When we have only one neighbor, that is in the denominator for kappa 2. So when we have two neighbors, then that gives nothing, no contribution. And this is a rational expression. We consider the Taylor expression, formal Taylor expression, expansion, and then then that is a series. We write in this form. Again, these L primes are rational entries here usually, and that is, and actually this is called a topological equivariant. Immediately we see that was the difference, the equivariant Poincaré series, topological Poincaré series. And if we separate exactly those coefficients L prime, which are integers, all the entries are integral, then that is the, say, the topological Poincaré series, what today I will consider. Actually, even analytically, we can define an equivariant topological, which would correspond with this when we allow also rational coefficients. But if I want analytically to define the analytic Poincaré, analytic Hilbert, then we have to go to the universal abelian covering. We have to consider the Hilbert, the Galois action on it, and then with some construction, we can extend the previous construction, what I consider for Hilbert and Poincaré analytic versions, also an equivalent version, and that would correspond with this one. And but here we defined only the, say, the corresponding to the trivial spin-6 structure or corresponding to the, say, just for the local ring of the original local ring. And because of that reason, this equivariant P, we have to simplify a little bit. We consider only those coefficients, that part of the series which is supported by integral coefficients, integral lattice. So this is a topological candidate. That is the topological candidate of our PT. So right now, what we have, again, let's try let's see what we have. So we have an analytic type, singularity. We define the Hilbert function using the filtration. From the Hilbert, we computed the PT. Then, using the resolution graph completely independently, we defined this, yes, using this generating function, yes, somehow. And we defined a topological from the combinatorial Poincaré. We call Poincaré, but zeta functions, basically topological combinatorial zeta function from the resolution graph. So what is the point? The point is that, yes, so here we have the analytic objects, and here from topology, from the graph, we defined another one. And there is a theorem which tells us that if the analytic type is not very complicated, it's nice in some sense. And here I put it some analytic types of some names. So if X is rational, so that means that the geometric genus is 0, or it's minimal elliptic, or weighted homogeneous. So I didn't plan now to define all of them, but I'm sure that most of everybody knows these definitions, that what is an analytic singularity, or what in the analytic surface singularity when is rational or elliptic or weighted homogeneous. So if in these situations, for example, rational means, for example, all the quotient singularities are rational, or the ADE singularities are rational. So in all these cases, actually, the analytically defined PT is equals the topologically defined, combinatorially defined PT. So that is the connection. That's why we say that we have to go to the Poincaré, and then hopefully the Poincaré can be linked by the topology. So the topology here is that topologically we define the zeta functions, and in some cases, and that is a very large class actually, then we have PT, the analytically defined Poincaré equals is this topologically defined PT. Actually, we can even identify the maximum family, that family which when we have exactly this P equals P topological. So PT equals P topological, so that combinatorial defined, that is using the divisorial filtration, if and only if X is a splice quotient singularity. Again, I don't plan to introduce the definition, precise definition of splice quotient singularities. Was introduced originally by Neumann and Wall. So what's the point here is that you fix a resolution graph, which is a negative definite intersection matrix, yes, which is a candidate for a normal surface singularity. We fix a resolution graph, plumbing graph, say negative definite plumbing graph. And then using that graph, you define combinatorially from that graph, you extract some monomial, and you define some equations. And that those equations, they have some ambiguity, but it defines an equisingular family of singularities, and they are called splice quotients. And for those splice quotient singularities, because they are defined using gamma, the graph, there is of course, there is a hope that also the analytic type, it somehow it preserves a lot of topological, so it's somehow the analytic invariance can be recovered from topology. Then indeed, for those singularities, this identity holds. So, but I want to discuss also a little bit more about this. So let's see again just what are the conclusions sort of exactly in this family. For these large families, or either you consider just this rational minimal elliptic weighted homogeneous, even for weighted homogeneous germ, this identity is not evident at all. So it's very deep. So if we assume that the analytic type is nice in this point, from this point of view, then we have this identity given by the theorem. Then from inversion theorem, what we discussed that works in any case, we recover H, then we recover a lot of, yes, shift theoretical invariance. So for example, if I just go to the previous formula, what I mentioned using HL and H1 connections and PG, then if I write that formula, then what we have now additionally? We have additionally that HL can be recovered from the graph by these steps, yes. Then this term here is topological, chi of L is topological, and let's see what is happening with H1. If L is large in the Lippmann cone, yes, somehow it's in a vanishing zone. It's like in the local version of Kodaira vanishing theorem. So when you L is and also that vanishing zone is topologically you can identify. Yes, it's that K minus K plus the Lippmann cone, so it can be identified. If L is there, then you have a vanishing theorem. Then this term H1 is 0. Then what we have, then PG is topological. PG can be computed as chi of L. So here's the formula. The PG is chi of L minus chi of L in HL, the Hilbert coefficient. This expression is from the graph. HL is from this inversion formula from the topological Poincaré. So then we have that surprise PG can be computed from the resolution graph. Of course, that is theoretically we have here that, okay, in principle can be computed, but it's not so evident that what is it. So even if we prove that it's topological, then it's not so evident that what is now the concrete. So it's some other topological expression of it. Well, in this case, turns out that in these splice quotient singularities, it's not just that it's topological, say theoretically that can be computed using the graph, but it actually is a Seiberg-Witten invariant of the link. So these are somehow the steps what we want to follow. So we attack, say, an analytic invariant, and we want to find the pair, its pair. And sometimes, of course, that when we have nice singularities, then it's exactly by this identity we can go connect the topology with analytic invariance by this identification of the topological Poincaré and analytic Poincaré, and after that the inversion formula. Well, now is the next what I want to discuss, and that's can be very interesting because of the also from topological point of view. Because so let's discuss the following problem. So if I consider an arbitrary analytic type, then it can happen that the analytic Poincaré is not the same as the topological Poincaré. This Poincaré, topological Poincaré, I define somehow, and you can ask me that why exactly I use this expression. Well, this is somehow it's very similar as the Poincaré series of say weighted homogeneous complete intersections, or yes, it's and on the other hand also the splice quotient singularities are somehow not very far from that, and that's why here we use a very special zeta function type candidate for the combinatorial version, yes, for the PT, but of course that if the analytic type is completely different, it's very bad, say, then there is no hope that say topology, so that the two Poincaré series will coincide. So here's the question. So let's fix the topological type. That means that we fix, say, the link, or we fix a resolution graph. Yes, we fix a resolution graph or the three manifold, the link. And then we consider all the analytic types. Yes, the analytic types supported on that topological type. Where sometimes this is only one. Say in the case of ADE, there is only one. So in that case, we basically solve. We already know that was the answer. But if the analytic type might jump, yes, then in that case, we have for different analytic types, different analytic Poincaré series. And of course that they cannot all of them be the same with the P topological. So that's the question, that what are the possible series P of T? Yes, when we vary the analytic type. Of course that this is a very deep analytic question. Even the classification of analytic types, even if that what type of space, that moduli space, what it is, can be very hard. It is very hard. And then after that, for all the possibilities, that has a very interesting stratification. And of course that on the equisingularity move, yes, strata, that will be the same PT, but we will have a finitely many PTs associated with the stratification. So we have a finitely many series, yes, associated with the possible analytic structures. And I'm really interested in this because I really hope that, or I think that also from topological point of view can be interesting, that if I fix the resolution graph or that three manifold, this collection of series might tell something about the topology, might produce something. For example, here this what I considered here in the previous pages, this zeta function, what I consider, that is related with the Seiberg-Witten invariant. Well, what is the other ones? If I consider all the analytic types, I consider the Poincarés, I will have a family, or I have a collection of multivariable series. Do they codify anything important from the topological point of view? I believe that yes, and it really would be will be very important to find this family. I believe that also from an analytic point of view, but also from topological point of view. So this would be a very interesting question, and hopefully topologists also consider that is important, not just myself. Well, let's discuss another problem. So just to suggest that not only this P topological, these zeta functions, what I wrote here. So here I defined in this way, and this was great for many analytic types, and it was connections. Later I will come back also to the Seiberg-Witten. So this is a jolly joker. It's a very nice topological zeta function. On the other hand, just let's consider this family of Karp singularities. This is not rational homogeneous, but it's maybe the very first singularity or very first graph, which is not the three manifold. It's not the simplest one when it's not rational homogeneous. So that is just a loop of vertices. So if I consider vertex, any vertex has exactly two neighbors. And of course, that in my case, I'm interested only in the negative definite situation. so all the exception curves are pi1 and all the valencies are 2. And in this case, the link, the three manifold is a torus bundle over S1, and the monodromy of the torus bundle can be computed using the graph. So it's a very interesting combinatorics, but it's not very, very complicated. It's well known. And well, just let's see that what we have from the old formula. If I have the topological, what I just used, the zeta function, that topological formula is just trivial, nothing, because all the valencies are 2. This expression gives nothing. So in this case, we don't have this candidate gives nothing. On the other hand, of course, we know that here it's an analytic type. We have the Hilbert function, we have a Poincaré. So question, what is now the polynomial, the Poincaré polynomial? So exactly what is this PT? So right now, of course, we cannot say that will be this one, because the right-hand side, the topological, it's trivial, but of course that we try to compute. And here is the theorem that the PT in this case again can be computed from the graph, and it's a nice expression, but it's completely different. So that's why I want to suggest that if in different analytic situations, we might have for the Poincaré different expressions for PT. And it will be, for example, it's very interesting in this case, in the case of CAS, so it's a torus bundle from topological point of view. We can forget about the singularity. Just consider the torus bundle over S1. Yes, the monodromy can be expressed using the graph, or yes, some continued fraction expression. And then we consider also in that intersection matrix, we consider the dual. Yes, the dual elements, base elements. We write this PT, we make the Taylor expansion, and that is PT. What is the connection with the topology? Can anybody tell the topological meaning of this? Or later we will see that the asymptotic behavior of this will be the Seiberg-Witten or will be some other topological invariant. What topological invariant can be connected with this PT? Maybe going back to the previous page, that any analytic type, maybe analytic will give a PT, and any PT, such PT will be connected with some topological invariant, yes, which has some intim connections or some which with that analytic type. So that's the goal, hope, or just I don't know. It's a question. Actually, this generating function, which appears here, it's very surprisingly appears in also in commutative. So it's some interesting ideas. That is a Poincaré series of some completely in a different area actually was considered. So it can be that also in topology we'll have some appearance. So let's see. No, just
where was it considered? What?
Actually, in some ideas, so some, if you go to the combinatorial algebra, commutative algebra, I can send to you some references for this. Okay. So the Poincaré of some interesting algebras and then the ideas. So let's see. Yeah, maybe here again, just to this slide. So just to mention that just to give an idea that how it can happen that I fix a topological type and I have many different analytic structures and probably many different analytic Poincaré series. So let's consider this topological type. Yes, so that is an integral homology sphere given by this resolution graph or this plumbing graph. And actually actually with Tomohiro Okuma, we try to classify to see the possible analytic structures supported by on this. And actually this is our classification. Actually there are the stratification of the moduli space has 3 strata. And the generic one, the generic analytic structure that has the PG, the minimum possible given by this graph, that is PG2. And actually 2 special analytic structures, the Kulikov of Kodaira, again, I will not define, but that is somehow very interesting analytic type, non-Gorenstein, and also this has also splice quotient or Gorenstein or complete intersection analytic type. Actually, it's in C4 given by two equations, and both of them PG3. But for all of them, the analytic Poincaré, they are completely different. The splice quotient, the second here, actually that coincides with the what I define the zeta function topological, but the other ones are completely different. For the generic one again can be defined. We actually using this article with my student Nagy János, we know all the invariants of generic analysis structure, what is needed. We computed the Hilbert, the HS. So that is again known. For the Kodaira-Kulikov, we didn't compute yet, but probably somebody or my student or myself, I will compute. But anyway, so here is the list that here probably 3 different Poincaré series play an important role, and not only just this zeta function, what we already considered. So let's, one more, what just I want to, about this analytic and topological game. So again, we have here HT and PT, the analytic part. We define by inversion formula from PL. And let's go to the topological inversion. So topological invariance, we have the zeta function from the graph. We consider the coefficients, and blindly, just as we did in the analytic type, using exactly the same summation formula, I defined the Hilbert coefficients, say, of the topological object. Again, that's also true that the topological Poincaré is supported by the first, by the Lippmann cone, by the cone in the first quadrant, because exactly the EI stars generate the Lippmann cone. So actually, this summation is finite, makes sense, so I can consider this. So these are exactly somehow using these zeta functions, the topological candidates. And let's compare them from analytic discussion. So there is a theorem which tells you that the asymptotic behavior, so if L is very large in the Lippmann cone, then H of L behaves like this. Actually, I already considered this, yes? So it's a quadratic function, actually that is topological, but its PG is the free term, is analytic invariant, and that is the asymptotic behavior of the analytic Hilbert function. If I define the topological, starting from this zeta function, using the same inversion formula blindly, then it turns out that actually we can write to say that this is somehow counting function of the coefficients of the Poincaré, yes, and then counting in a tricky way in this shape, yes. Well, if we make the counting function in that way, then for L, again, big in the Lippmann cone, H of L behaves asymptotically, is the same chi of L, the Riemann-Roch expression, and the free term is the normalized Seiberg-Witten invariant of the link. So, and again, the question is, if I replace this topological invariant by some other topologic, what kind of other series I can put here in such a way that, say, the asymptotic behavior, the free term gives a famous topological invariant? There are some other ones or not, or these ones which come from the different analytic structures, say, do they provide anything nice topologically? That is the question. So this is my talk. I finished my talk. And
any questions for the audience here?
I have a question. Is there a connection with, I think it's called the E polynomial?
E polynomial.
Yeah, which.
So that is the Hilbert, the Hodge structure. That's
yeah,
what
exactly. It's determined by the mixed Hodge structure.
Well, you see, I tell you another connection. I wrote nothing here about that, but the interesting thing is I start with a resolution. Yes, and yes, and using some machinery, of course, that here I defined the filtration. Yes, I defined the filtration for any L. I defined an ideal, say in the analytic side. Yes, in the analytic side, an ideal, and that we have the Hilbert coefficient. On the other hand, if you make a more complicated, a little bit more complex construction, then for any lattice point, each of any lattice point L, you can define some kind of linear subspace arrangement. Yes, for any L, you have a linear subspace arrangement from the analytic type. Also, from the topological type, somehow from any L, you have a linear subspace arrangement. And the important thing is that if I can consider the topological Euler, the usual Euler characteristic of the linear subspace arrangement on the analytic side, that coefficient is P of L, the analytic coefficient. If I go to the topological subspace arrangement, then the Euler characteristic of the complement of the subspace arrangement will be the topological PT, P of L. Well, but why I'm saying this, that once you have these subspace arrangements, yes, and here what we consider the Euler character, topological Euler characteristic of the complement, this complement actually is an algebraic, it's a quasi-projective space. You can consider this object in the Grothendieck ring. So also for both cases, for the analytic type, you have basically improvement. Actually, it's a motivic P, which uses in the Grothendieck coefficients in the Grothendieck ring. For each L, you have an object in the Grothendieck ring. P of L is replaced by an element in the Grothendieck ring. Also in the topological version, you have here an element in the Grothendieck ring. Well, that's already, you see, it's a little bit in the direction of the E, because you have the Grothendieck ring. You don't go to the topological Euler characteristic, but you go to the E functor, yes? And you have a version in the E version, yes, E version of all these. So everything can be lifted to the E level, what you just asked. But even to the Grothendieck, yes, to the Grothendieck ring can be lifted. I don't know if this answers or not. That is, say, one of the connections what can be done in that direction. But it's immediate, almost on these pages. But of course, there is an additional construction which provides somehow the arrangements. And yeah.
Questions?
Maybe some other.
Yeah, can I ask something?
Sure.
So, for example, how much does this invariance change when you consider a complete smooth surface in a divisor on it in such a way that the boundary of a tubular neighborhood is, let's say, a homology sphere? So how much depends on the negativity of the intersection matrix? Can you, can you say something in the non-negative
I understand
case?
where you want to ask that if the topology, if the link is integral homology sphere, if that has an effect on everything. Is that the question?
But I'm asking in a global situation of
Yeah.
from a
Yes,
divisor,
yes,
not coming from a singularity.
Yeah. You see, you can define it's these.
Yeah.
Both of them have their global analog. So if you take, yes, you are interested in fine spaces, and you take the compactification, yes, at infinity, you can consider the divisors at infinity. That has a filtration of the global functions. Of course, that you can, then maybe you have to consider some line boundaries, not the global functions, because maybe the global functions are too small, too pure to have the filtration there. But in some sections, some good line boundaries, then you will have a filtration. So also the global version has an analog. It's I'm sure that has an analog. And also, if we we concentrate on this zeta function, what is in the topological side, that is just combinatorics. That once you have the graph, you see the graph of the divisor at infinity, this can be defined. What you need, say, blindly, if we just want to continue this or to extend this, what was needed is that the intersection matrix is definite, and not definite. It's non-degenerate, because then you already have the dual basis. You don't really need that it's even if it's not negative definite, this can be defined. Of course, that probably then it will be not true that this will be in some nice cone, but even that maybe can be checked. Or maybe will be not so thin, that cone maybe will be bigger, but yes. So also the combinatorial part can be defined. Also I'm sure that also the analytic type can be defined using the divisorial filtration.
Yeah.
On some good object, maybe not the A0 of the global of the structure sheet, but on some line bundle.
I see. Thank
But
you.
also here, the equivalent version, it's exactly the extension of some line bundles, the filtration of some line bundles, given by natural line bundles, given by the universal Billion covering. So this has, even in the local case, the version when we consider the filtration on line bundles, yes, on some important line bundles. So that globally, I'm sure that it's. The question is that, again, if we see the connections, we can relate the topology with the analytic, and you find that if indeed, if we define in this way the topological type, then that gives some nice connections with some topological, classical, or modern, or I don't know, other type of topological invariants.
Nice. Thank you.
Well, thank you so much then for an excellent talk.